Hi guys, you are welcome once again to the Smart Way lectures on the Science Ambassador series. This is a series of lectures we are running on all the areas in science, and today we are here with you to continue on thermochemistry, also called energy changes. In our last lectures, we look at the theory on the standard enthalpy of neutralization. We said that standard enthalpy of neutralization is the energy liberated when 1 mole of a strong acid reacts with a 1 mole of a strong base. Again, we said that standard enthalpy is the energy liberated when 1 mole of a strong acid, 1 mole of a strong acid reacts with a 1 mole of a strong base, okay, at standard conditions. And the standard conditions are usually at 298 Kelvin and 1 atm. And these are the three reactions that I gave in our last lectures. I gave you the sodium hydroxide, I gave you the hydrogen chloride combined with the sodium hydroxide, and the hydrogen nitrate combined with the sodium hydroxide. And this time I'm using the sodium hydrogen hydride combined with the potassium hydroxide. Now in this reaction, 1 mole of each of the acid and base were added, and the amount of energy liberated to the surrounding, okay, was found to almost have the same value. So the first one, when you add 1 mole of strong ACl to 1 mole of strong sodium hydroxide base, this is the value that, okay, is found to be liberated. It is in kilojoules per mole. And for hydrogen nitrate, when you also add 1 mole of that, you also get the same thing, okay. And when you also add the hydrogen iodide, okay, plus the potassium hydroxide, strong acid, strong base, 1 mole each, you almost get the same value. So the values, okay, that, okay, we get are the values of energy that is liberated to the surrounding. And so we observe that in the reactions, okay, 1 mole of water, okay, is produced from each of the reactions. So you can see from here that 1 mole of water here is produced. You can see that here, you can see that 1 mole here is produced here, and then 1 mole here is also produced, and also 1 mole is also produced here. So in each of these reactions, you realize that 1 mole of water is produced. And so we defined standard enthalpy of neutralization with respect to the formation of 1 mole of water. So we can also say that instead of saying that it is the amount of energy liberated by reacting 1 mole of a strong acid to 1 mole of a strong base, okay, under standard condition, you can also say that it is the amount of energy liberated when 1 mole of water is formed, okay, from H plus ion coming from an acid, and then OH minus coming from what? A base. That is, it is, once again, you can also define it in terms of the mole of water form from the three reactions when strong acid and strong base, okay, was combined in with 1 mole each. The same mole of water was what produced, and the same energy was what produced or liberated at the end. So we can also define it in terms of formation of water from its what? Ions. From its ions. We can also define it as the energy liberated when 1 mole of water is formed from its ions, that is the H plus, okay, coming from the acid, and then the OH minus coming from what? From the base. So we also define it like that. This, okay, has the same value as that. And then we also went on to say that the values of the enthalpy that we get when we add weak acid and a strong base are not the same as adding strong acid to what? A strong base. So here you realize that when you add weak acid to a strong base, the value you get a less what? Enthalpy from the reaction, okay. And again, when you add a strong acid to what? A weak base, you also get a less enthalpy. The weakest of it is when you add the weak acid to a weak base, you also get the least enthalpy. Now we explain this, okay, in terms of the fact that for weak acid do not dissociate completely in reactions, and so they do not complete the reaction. Some of this acid remain in the what? In the reaction vessel. And so for a complete what? Dissociation of a weak acid, usually some amount of energy is required to further break down the undissociated what? A weak acid in the what? In the reaction. This causes what? The amount of energy liberated, okay, to be less as compared to the energy liberated when strong acid and a strong base. Energy is absorbed that is an endothermic reaction takes place, energy is absorbed into the reaction to further break down the undissociated weak acid to complete the reaction. This tends to limit or reduce the total amount of energy liberated to the surrounding. So instead of 57.5 kilogram per mole of energy liberated to the surrounding, some part of the 57.5 kilojoules per mole is used in bond breaking, for the weak acid. Hence the total energy that will be released from the reaction is less. Again, now this also happens for a weak base reacting with a strong acid. Weak base do not break down completely, and so there is amount of energy absorbed into the reaction to further cause the remaining base to break down. This limit or reduce the total amount of energy that is supposed to be liberated to the surrounding. Now this also happens for a weak acid and a weak base. Now for a weak acid and a weak base, the molecules do not break down completely. Some still remains in the solution, and so energy is absorbed from the surrounding in order to break down the weak molecules of the acid and the base. This cause a total reduction of the net energy that is supposed to be liberated. Now quickly let me give you some examples of the weak acid and the weak base. Then we will continue on this lecture on enthalpy of neutralization, that is how to experimentally measure it. Good. So in our last lecture I didn't give you the examples of weak acid and a weak base. So these are examples of weak acids. So let me write this one quickly. Weak acids. So weak acids, very simple. It is one, we have all organic acids are weak acids. So let me write all organic acids. That is, all organic acids are weak acids. Usually organic acids are arachidonic acids. They are called the arachidonic acids. So we have what we call the ethanoic acid. Ethanoic acid. All organic acids are weak acids. So ethanoic acid is a weak acid. The propanoic acid is also a weak acid. Propanoic acid is also a weak acid. So we have ethanoic acid. We have propanoic acid. We have the butanoic acid. These are all weak acids. Every organic acid is a weak acid. So we have methanoic acid, propanoic acid, pentanoic acid, and all. Ethanoic means 2 carbons. So we are going to get S, that is CH3, COOH, that is 2 carbons. So and the signature for all organic acid is what? Is this. The signature for all organic acid is COOH. Good, COOH. And so for ethanoic it must be 2 carbons. So 2 carbon, we have 1 carbon added to this one to become ethanoic acid. And we also have what we call the propanoic acid. Propanoic is 3 carbon. So we have CH3, we have CH2, and then the last C will be for the functional group, that's COOH. Then let me give you the last one. For the butanoic acid is 4 carbon. So we have the CH3, the CH2, the CH2 again, and then the last carbon taken by the functional group. That is the functional group. So these are all. So all organic acids are weak acid. Other weak acids that we have is hydrogen cyanide. We have hydrogen cyanide is one. And then we also have what we call hydrogen carbonate. It's also a weak acid. Hydrogen carbonate is also a weak acid. So these are all examples of weak acids. All examples. So whenever they give you these acids, realize that the enthalpy change for the reactions are always less. Now let me quickly give the weak base. For the weak base, they are hydroxides of group 3 and group 4, and the transition metals. So hydroxide of group 3 and group 4 and transition metals. So for weak base, we are going to get hydroxides of weak base. So I'm talking about hydroxides of. For weak base, we have hydroxides of what? Hydroxides of group 1 metals, group 3 metals, group 4 metals, and our transition metals. Okay, our transition metals. Okay, transition metals. And we know that our the group 3 metal is what? Aluminium. And again, group 4 metal is what? Is silicon. And transition metals, we have the copper, we have the zinc, we have the iron. So when you combine hydroxide with them, for example, you get aluminium. The valency for aluminium is 3, and so the 3 will cross to become 3 under there. And then we also have the silicon hydroxide. The valence, the charge for what? The silicon is 4, and so but when they are forming compound, they exchange, and so we are going to get also 4 over here. So these are all examples of that. I can go on to add this. Good. So I can go on to give you other ones like the zinc hydroxide. We have the copper hydroxide. These are all weak what? Base. These are all weak base. So for hydroxide, it's very simple. Metals of group 3, the hydroxides of group 3 and the group 4, and all transition metals. For weak acids, they are all organic acids, including the hydrogen cyanide and then the hydrogen carbonate. So these are examples of the things that we did in our last lecture. Here we are going to look at the experimental determination of, we are going to quantify the heat that is supposed to be liberated when 1 mole of acid reacts with 1 mole of base. Good. Now to do that, this is very simple. All you need is to first ensure that the initial temperatures of both the acid and base in their respective mediums are the same. Here the base is in the beaker and then the acid is in the calorimeter. Okay, so make sure that the temperatures of both the acid and the base are the same in their respective medium. Good. The next is to transfer a certain volume of the base from the beaker of a particular concentration into the calorimeter containing the acid. Now, the calorimeter must be weighed to know the mass, and must come with what? A known specific heat capacity, like this one. So known mass and a known specific capacity. Now, the final temperature after the addition is what? Is taken. The final temperature after addition is taken. When this base comes into contact with the acid, there will be what we call salt solution. And so you take what we call the final temperature. When the base comes into contact with the acid, there is a reaction. This reaction gives off heat to the surrounding. And the temperature helps us to recall the heat that is given out in the process. So you recall the final temperature. So this is what we do. Very simple. Here, after that, you weigh the calorimeter again. That is to measure the mass of the salt solution formed. You weigh the calorimeter, okay, after the addition to measure the mass of the solution that is formed. So that is how to do that. First step is to ensure that the temperatures, okay, are the same for both the acid and base in their respective medium. Second is to pour a certain volume of the base, okay, from the beaker into the acid in the conical flask. Now you then take the final temperature, because yes, when the base comes into contact with the acid, it is now transformed into what we call a salt solution. So you take what we call the final temperature and then weigh the calorimeter again. Now after recording the final temperature, all you need to do is to weigh the calorimeter and then take the final mass again, okay? To weigh the calorimeter and then take the final mass again. So quickly, that's what we do. So let's put our parameters down and then let's quickly do that. Let's put our parameters down. Now, from the reaction, we reacted what? From the reaction, we reacted sodium hydroxide plus what? HCl. And in the reaction, we got sodium chloride plus water. This is the salt solution. So here a certain volume of the base was poured, okay, onto a certain volume of the acid of the same concentration, 1 molar. Now the initial temperatures were taken, and after it was poured, the final temperature was taken. Okay, so we'll do that. So this is what we did, and the parameters, okay, are one, we want to know the heat of the reaction, but realize that the acid and base will give up heat. When acid reacts with base, there is heat that is what giving off to the surrounding. That's where that's what the thermometer will capture. So here the heat, okay, lost by the acid, okay, and the base during the reaction, the heat lost by the acid and base during the reaction, acid and base, during the reaction is equal to the heat what gained by the water, and the surrounding, gained by the water and the surrounding. So heat gained by the water and the surrounding, by the water and the surrounding. Here, what is surrounding the water? The copper is surrounding the water, so plus the heat gained by the copper. Heat was gained by the copper. Heat gained by copper. Heat gained by copper. So when you bring the acid and base, okay, together, though it will evolve or liberate heat. The heat will be given to the surrounding, and the water is the first, okay, surrounding of the acid, and then it will also be gained by the what, the whatever is surrounding the water. Okay, so the acid and base were brought together. Reactions are taking place in the water, and these reactions are giving off heat, and the water is taking the heat. And because copper is also surrounding the water, the copper also takes some amount of heat. So the heat given off, okay, during the combination of the acid and base is proportional to the heat taken by the water plus the heat taken by the copper calorimeter. Now, it is this quantity of heat that we are going to divide by the mole of either the water produced or the mole of either the water produced or the mole of the acid or base used. So basically that's what we are going to do. So it's either the mole of the water produced or the base that is used. So let's use the mole of the acid. Let's use the mole of the acid. Okay, so we are going to do that. So quickly, now in our last lecture I told you that the formula for heat change is the same as what? The specific capacity times mass times what? Change in what? In temperature, times mass times change in what? In temperature. So quickly, we are going to use that formula to do that. So quickly, now our enthalpy of neutralization, the enthalpy of neutralization we are looking for in this reaction, once again, the standard enthalpy of neutralization we are looking for once again is given by the heat gained by the water plus the heat what gained by the what? The heat gained by the water plus the heat gained by the copper, all divided by the heat, all divided by the mole, all divided by the mole of either the water form or the acid use. Okay, so this is the formula. So quickly, let's do that. Now, how do we determine the heat gained by the water? It's very simple. We know the mass of the water, we know the specific capacity of the water, so we multiply the specific capacity of the water times the mass of the water, okay, that is form, times the what, times the change in what, in temperature, that is T1, or that is T1 minus T2, or T2 minus T1, and then you add it to what, the heat, you then add it to the heat gained by the copper, and the heat gained by the copper, you do it by looking at the specific capacity of the copper. Okay, you multiply the specific capacity of the copper times the mass of the what, mass of the copper times again change in temperature of the what of the whole solution. So, and all this divided by the mole of the mole of that gold by the mole of that. So this is what to do. Here, what do we know? We know that the quantity of water that will be produced, okay, after the reaction will dominate the what? The salt. And so instead of looking at the heat gained by the salt solution, I'm using the heat gained by the water. Okay, I'm using the heat gained by the water. So please, this is because the quantity of heat, the salt that will be produced at the end of the day, okay, is small. That will be dominated by the water, and so that is the density will be still close. Okay, the density of the solution, that is the salt solution, will be close to the what? To the water. And so basically, we use the what? We assume that the salt solution is now the water. Please, this is based on the fact that the quantity of the salt solution, that is produced is small, and so the density of the water is still close to what? Water. And so we usually use the what? The water instead of what? Calculating the heat gained by the salt solution. Okay, which the right one is we should have used the heat gained by the salt solution. But this time we are using heat gained by the what? By the water. Now realize that the acid and base came together, they produced what? Salt solution. They didn't produce what? Only water. They produced a salt solution. But we are saying that the salt that is produced, okay, is small. The resulting solution is dilute. So the density is still close to water. So we can use the water as the what? We can use the heat gained by the water as the heat gained by the salt solution. So this is the assumption that I am making. Good. To find the mass of the water produced here, from here to find the mass of the water produced, it's very simple. You have to use what we call the density. Density is equal to what? Mass over what? Over volume. And so you realize that mass is proportional to D times what? Times V. And so you have to know the what? The density. We know the density already to be what? To be 1. And then the total volume for the two solutions, the total volumes of the two solutions. Here we use what? Here we use X volume of the base, and we added it to X volume of the what? Of the acid. So the total volume of the acid and base will be proportional to the volume of the water. Okay, the total volume of both the acid and base when brought together will be proportional to the volume of water. Realize that the base, okay, is dilute, and then the acid is also dilute. So largely it is equal to what? The volume of the base solution and the volume of the acid solution is basically water. And so the total solution, the total volume of the two solutions will be proportional to the volume of the water that is produced at the end of the day. So quickly, we do that by looking at this. We do that by looking at, we add the X, okay, S cube of the base plus what? S cube of the what? Of the acid. So here, what are you going to get? You are going to get 2 what? 2x raised to the power what? 3. Okay, that is 2s raised to the power 3. These are the total volumes. Now to do that, we are going to get m equal to find the mass of the water. Now to find the mass of the water, you multiply the density. Good. You multiply the what? The density, okay, times what? You multiply the density times 2x cube. Okay, that is the total volume of the water. That is the total volume of the water. Now, since the density of water is 1, when you multiply, we are still going to get 2x what? G. Okay, remember that the density of water is 1, so D equal to what? Is 1. That is 1 gram per cm cube. Have you gotten that? So when you multiply 1 gram per cm cube to 2x cm cube, you realize that this will cancel this one, and then you will still get the same value. Let me do it for you so that you understand. Good. Let me do it for you. Realize that the density of water is 1 gram per cm cube, and then we have the total volume to be what? 2 what? X cm cube. Okay. So what do we know? Cm cube cancels cm cube, and then the total volume becomes the total mass. The total volume becomes the total mass. So here we have been able to calculate for the mass of the water. We have been able to calculate for the mass of water. The change in temperature you will know from there, and then the mass of the calorimeter you know. The last one is to also look at the mole of the acid that is produced. So the mole of the acid. How do we know the mole of the acid? Very simple. Okay. Here I want to find the mole of the acid that was neutralized. Okay. Mole of the acid that was neutralized. So mole of the acid that was neutralized, we know that it is the same as concentration times what? Times volume. Have you gotten that? So quickly, what are we going to do? We are going to get concentration times what? Times volume. Okay. That is concentration of the acid. That is the concentration of the what? Of the acid times what? Times the volume of the acid. Good. So here we are going to use 1 mole per dm cube. And then here we use what we call cm cube. But you know that cm cube is always converted. So you convert the cm cube to dm cube. Okay. So multiply by the volume, divided by what? By 1000. So divide this one by 1000. Okay. That is, you divide this by 1000. So you divide here by the x volume by what? By 1000. Okay. By 1000. So when you divide x volume by 1000, you realize that you are going to get 0.001 what? Mole. Okay, so 0.001 mole. Good. So quickly here, the enthalpy of neutralization. So quickly here, enthalpy of neutralization. The enthalpy of neutralization of the 1 mole of the acid is proportional to, good, just as we have written here. Okay. Yeah, so this is the main formula. Okay, and these are the deductions that we have made. So quickly we are going to get this. So quickly we are going to get what? We are going to get C W times what? The mass of water. Now we know the mass of water to be what? 2x grams. We know the mass of water to be 2x grams, and then times the what? Times the change in what? In temperature. Okay, and then you add it to the specific capacity of the water, and then add it to the specific capacity of the calorimeter. So you are going to get specific capacity of the calorimeter times mass of calorimeter. That is when you weigh, you do your subtraction. Okay, and then times the what? The change in what? In temperature. Then over the mole of the what? Of the salt used. So here, when we did everything, realize that the mole of everything that we use now is this. The mole of everything that we used that was 0.001x. Please, it's 1x rather. So 0.001x mole. Okay. So this is what you do, and then you find that, and then you realize that here the unit of this will be what? Will be joules. Okay. And here the unit of this, it will be what? Will be mole. That is why enthalpy is always in what? Kilowatt joules per mole. That is why. So the heat divided by the mole, and so you get the answer. So we'll end our lecture here, and in our next episode we'll be looking at more questions. Thank you.